Happy Thursday afternoon. We're in part 3 of this particular, what I call lesson or unit or package or whatever you want to do it. That means we wrap it up and try to bring it into a broader significance. And as a reminder, the first unit is always about getting some information. The second unit is about taking some interpretation or doing some exercise with it. And then the third unit tries to bring it into the bigger picture. So for this particular one, we zoomed in on Lake Huron as an example of how to do a hydrological balance and some quantifications of what a drought or a longer term drought might look like. We could have done the same thing with the Sahara Lakes and worried about what conditions you would need to get lakes in the Sahara today. Algebra would be exactly the same. We would have set the equation up differently with different values, but that's fine. So without further ado, let's jump into a little bit of what we're going to do today. We're going to finish up that and review that. Today, I'm going to, after we get the Lake Huron exercise finished, I'm going to go through, stand back a little bit and talk about radiation a little bit more, because radiation controls the energy. And so we're going to jump scales from fairly small Lake Huron to the global perspective, because I'm going to come back to the question of why might those things be the same. And the argument I'll be making is that the radiation balance actually controls the wind patterns and circulation patterns. And if you chose, and some of you had suggested this, is if you change the wind circulation patterns, you're going to change the precipitation patterns, and conversely the drought patterns. And yeah, the answer is of course they can, or I wouldn't bring it up. This is the atmosphere. This is the unit. This is part of the system that moves a lot of energy around. The other one that moves most of the energy around is the ocean, and that's the topic of the next unit. So we'll see ocean circulations next time versus atmospheric circulations today. Before I go any further ado, any questions from you folks? I think when I evaluated stuff this morning, I forgot to post it or whatever, so it wasn't available to you for you to see if you look for it. It should be posted now, I think. Or it'll be posted pretty quickly. By and large, the exercise was a little bit, whoops, these are out of order. No, this isn't the right lecture. This isn't the right version. There we are. Emphasize that a lot of our frustration in this undertaking was merely dealing with the units. And units have got to be correct in any equation. And I don't know to the extent that you'll ever have to do that again, but it is a unit, in financial concerns, we're worried about what currency it is. So it's the same sort of principle. In general, you were asked to do some calculations. One way to improve those answers is, rather than just give the equation, is tell me what it means. Tell me what this number. Put some text behind it. The math gives you sort of the valid information that tells you you've got the answer, but put some text with it. Neither the text alone isn't going to convince you to understand it. The math will, but you could make it a little bit better by adding a little text. In the lecture, we divided question 2 into 2 parts. That never actually got transferred over to the question that you had on if you cut and paste the questions. So some folks, we had a little glitchy on whether you had to do 2 parts, and the 2 parts was an analysis. Part 1 was just do the hydrology today, balance today. Found out it's not 0 today, that's no surprise. The next thing we went down is we threw away the lakes, and we just tried to get a balance if we only had precipitation and evaporation of today's values, and we got that number. And then the second part of that exercise, after you throw out the influence of the rivers, the second part of that exercise was, well, let's find out what the balance really should be. How do we monkey around with a number? And you can monkey around with one of 2. And I systematically said monkey around with this one and monkey around with that one. Turns out the numbers are so close, you get sort of the same relationship, particularly if you've got an older version of the data we offered, because the spreadsheets rounded it up, so they got rid of the significant parts. Quite a range of questions, answers on question 3. That wasn't I think the comments that I've made individually were, should help you along. If there's not any questions, let me know. The bonus question is a bonus question means it's tricky. They're always going to be tricky. The question, if you read it real carefully, is not why it might have had a different hydrological balance. How can you find out of the two possibilities we examined which one was right? That's sort of another level of understanding or a little bit deeper question. And so I'm prone in the bonus questions to be a little more opaque than I am regular questions. I won't be that nasty on, but bonus questions, you know, I get that those are points, those are real points. So be careful about, always, general, read the question very carefully. This is probably, I will not say that every question that I've asked in all of these units is exactly clear cut. But, you know, question us if you're not comfortable with it, what it says, then give us an email and we'll get it out there. So anyway, the bonus question was to set up something, because today that's what we're going to talk about. Why could it happen? We'll delve into it a little more detail. If you've noticed a pattern, I asked a bonus question one day, a couple days later we talk about it. There's a somewhat method to that madness. Okay, energy. We've seen this before. It's basically about the Earth's radiation balance. And what's that involved? It's a different balance, but it's something about long-wave radiation coming in from the sun, giving us the energy, and then the short-wave radiation going back out of the atmosphere because the Earth is cooler than the sun. So the sun is 5,000 degrees heat. It radiates out a short wavelength. The Earth is, I don't remember exactly what it is, but it's not 5,000 degrees. And so the long wave radiations go out. The greenhouse gas is this little filtration thing where everything doesn't go up. It's actually only a small percent. It's like 15% or something. It's not a majority of the energy that goes out. The energy, most of the energy goes back up. You've got to, or the Earth wouldn't be in balance. It's in balance at a certain temperature. And remember that the black body radiation is the thing that you can monkey around with. You get more energy in here, it's going to heat up. The predictions of the warming, however valid they are for 100 years from now, or a warmer planet of some degree, well, the black body radiation is going to, oh, we've got more energy, we've got higher temperature, I'm going to spit off more energy. A very minor amount because we're talking about such large values. So there's an in and out, basically, there's several avenues to all of this. What I want to get sort of across at this point is that we have to do something with that energy. And we're going to do that in the atmosphere for today, and we'll probably do a similar exercise in the ocean next unit. If you dig into this, we had two arrows basically on the other one. Well, there's all kinds of arrows in here. That's the complexity of the planet. We're going to talk about the atmosphere today. We're going to kind of call it all the same thing. But the atmosphere has clouds in it, and it has a certain density contrast, and it has winds, and it has blah, 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 blah. So all of those things can go together in the energy budget. And what I want you, the take home from this particular slide is there's a lot of redirecting of energy. It's not all going in one simple arrow in one place. It gets bounced around and bounced around and bounced around. It doesn't get used up because you can't destroy energy necessarily, but it goes on different pathways. And specifically, the hard point, the first conceptual diagram is this. If I ask you where the warmest place on the planet is, you're going to say roughly where?
Europe.
Europe?
No, not Europe. Egypt.
Not necessarily the warmest place. What's the warmest region of the planet, basically? Close. Europe's closer than Egypt's closer than Europe was. Excuse me?
The equator?
The equator. Conceptually, it's the equator. And so this diagram explains why. So if we think of the energy coming from the sun as sort of a packet of energy, beep, 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 in it comes. And it hits the equator square on. So this gives you so many so much energy, and it's distributed over that amount of, that area. Well, all of the little packets coming from the sun are the same size, but how they hit the earth is very different. Here they hit it square on. Here they hit it at an angle, and in fact, you know, the angle up here is so much that it misses it entirely. Here the angle is spread out over a longer or wider area, if you will. And so this much energy here versus here is sort of like 2.5 times the amount of energy. So that's just the way the rays are coming in, and we get an intermediate value here and here, but this oblique angle is sort of the key take-home point. And it shows here, diffuse energy, concentrated energy, and then in the middle. So this diagram tells us that the energy is concentrated at the equator and decreases to the poles. If we go back to our basic physics, you can't have something get a whole lot hotter than someplace beside it. Energy always wants to go from where it is to where it's not. That's a fundamental principle in the universe. It wants to go from where it's concentrated to where it's not. So the short answer is, if we're getting 2.5 times as much energy here as here, which way is the energy want to move?
To where it's not.
Excuse me?
To where it's not.
Towards us?
To where it's not.
To where, which is, be specific.
Up.
No, this one's down. The poles,
Okay.
or we call them the high latitudes. So there's energy in the middle part of the planet, and where it's rotating, less so. Now, it's a little bit more complicated than that, because there's rotation, and there's different areas, and there's a tilt to it, and all that business. But that's the main take-home point. It wants to get out of here and go here. How can it do that? Well, glad you asked. This is another diagram shown the same way. I've got it cockeyed with the text, but here's the sun, here's the equator, here's that North Pole and the South Pole. And what we see here is average look at it. Average annual solar radiation absorbed, average annual emitted, right? This is the incoming versus outcoming. So at the red line is a lot of energy in the equator, less energy here. But look, if we talk about the stuff that goes back out, which is the blue area, there's not quite the contrast. Therefore, that tells us, in fact, that the energy is transferred from where it's in surplus to where it's in deficit. Okay, that's simple. Easy enough. And then how does it actually happen? I suspect that we have two fluids on this planet that can do this. Fluids are an easy way to move energy because they move. And one of them is called the atmosphere and one is called the ocean. If we thought about the Earth as a sphere, and I sometimes do this in class, and I'm tempted to do it in class here, and we say the energy's got to go from here to here, from here to here, or here to here, and I would ask you to draw the rays of that. I'm going to ask you to do that. Bring out a piece of paper or sketch on your iPad, a circle, and then just show me which way the energy is going to get from the hot area to the cold area. High energy, low energy, no problem. How does it actually, what pathway would it like to take? Remember that the Earth is a sphere and it's solid for our purposes. So that's one of these things where it's really easy once I show you the answer, but until when you fight about it, it's going to be for a while. That's good. How does it actually move from there? We're going to see convection, and I'm going to explain that all, and that's fine. But what does it really look like? So here's my Earth. Chalk is approved again this year, this week. A lot of energy here, it's piling up, it's piling up, it's piling up, it's piling up. It wants to get to here. How does it do it? First of all, can it go that way? That's the shortest path, it's the path of least resistance. Can't do it, why?
Solid, can't go through the solid.
So you can heat solids up and move heat through them.
It wouldn't move very fast.
It wouldn't move very fast at all.
We might get there one day.
Not in your lifetime.
Yeah.
So the solids are not the way to do it. Unfortunately, we have those two fluids. So the next question becomes, how would you draw a pathway involving, say, the atmosphere? Don't worry about the oceans right now. Consider this a solid sphere, put an atmosphere around it, some sort of fluid. And now what would the pathway look? The hint is something called convection. You're probably familiar with convection, the tea kettle on the upper right-hand side, heating it from below, not quite heating it from below, but the same difference. And what happens is what? The red arrows are the warm water rising. Do you know why the warm rises? Do you know why the warm water rises?
Is it like warm air just rises?
I'm sorry?
Warm air like rises in general? Warm air just rises in general?
It does in general, but yeah. Warm things in general in a fluid will rise. It's because when you warm things up, you expand the atoms and you make them less dense. And because you make them less dense, they flow up through the more dense things. Okay, that's tricky. But you can't have the water just accumulate up at the top forever and ever. This will give off its heat, or it will have to be replaced. If you're going to push water up here, you've got to replace it with something. So it sets up a cell to make that resupply. In this particular diagram, there's 3 cells in your tea kettle. The reality is if you made a tea kettle, it's probably 50 or 100 or something. It doesn't matter how many there are. But there's a pathway to make a full loop. And you'll just keep this up, heating this up, until this gets hot enough to start evaporating and making steam and drive it out the snout or whatever they call that thing and make the little whistle, right? So here's heating from the bottom. We're going to heat from the top. But we now want to, on our little sphere, put in the convection cells. They can't go through the green. So how would you draw them? We eliminated the green, and the question is, how are you going to draw them? Take a minute to wrestle with it, because it'll be more. How do they actually look conceptually? What's the first thing we want to start with? Where it's just hot. There. What's going to happen to the air when they land here, gets hot? What's going to happen to the land's going to get hot because it's getting the solar energy. What's going to happen to the air?
Air got wet.
It's going to what?
Wet.
Not necessarily west, it's going to get heat. Conceptually, it's going to heat up though, right? So we're going to transfer that energy to the air. And what's going to happen to that, the hot air? Same thing as the water here. What's going to happen to the hot air? Go ahead.
It'll rise.
It's going to rise. Okay, so the first thing it's going to do is have a rising. Oh, that's nice. What's going to happen to it next? It can't rise up forever, or we wouldn't breathe. We'd suffocate because all the hot air is gone. What's going to happen to it next? Oh, this is the one that gets most people. Yeah, don't worry. Got to go somewhere.
As it gets further away, the gravitational pull holds it in place, but it also gets colder, so it gets more dense at the top because it's further away from the heating land, and then it comes down again.
Where would you bring it down?
It will come down further away from where it's getting hit. So in this scenario, it would go down like below it.
I'm not sure I understand what you mean.
Because
Ask me to move the stick to show me where it's coming down.
Well, so you have the arrow coming up,
Yep.
right, out of the side. It'll come down around towards the poles,
Down
away
here.
from the equator, because the poles are colder, and it'll push the air up.
So you're arguing for something that looks like this?
Yeah.
Is there just one of those? Why?
Because it has to be.
So there's two of these puppies. And so he's exactly right. It rises up, can only go so far before it starts cooling off, and then it loses its ability to rise any further. And at that point, it becomes part of the cell, and it cools off conceptually and drops down where it's cold. And there has to be this return leg, otherwise you run out of air and die. So that's the trick. Now, in 3 dimensions, this is like, I don't know what the chemical, what the name is, but you've got to visualize, I've just drawn 1 dimension of it, but this envelope comes out around this side too. And it probably does it better than that, but. And so there's a whole envelope all the way around in and out of the water, around the sphere of the earth, conceptually. Okay? So that explains how we get a mechanism to get heat from the equator to the pole. And we're going to talk about, I want to give you some background in the atmosphere, because we're talking about that doing all of the work. This is an intriguing diagram. This is the radius of the earth. Here's the state of Florida for scale. They take this part of Florida and make this outline here, so that we get some sense of scale. So what this is telling me is this is all the way across Florida. Okay, now what I'm really interested in is not Florida, but what's happening as I go up from the surface of the planet. So it's just really perceptible, but here's the curvature of the earth. And we take one Florida width, and we go up in here, and they're talking about low altitude satellites. Up in here is where all the satellites are. Well, we walk up through a whole series of these layers, and we give them names. There's the crust of the earth, there's the troposphere, there's the stratosphere, mesosphere, thermosphere. They all have different properties and names. Here's Mount Everest. It's in the troposphere. Here's Manhattan, the Isle of Manhattan for scale. So it's, Manhattan's sort of long is about 2 Everests high. Or Manhattan is as deep as, is as long as the highest point on the globe to the deepest point on the globe-ish, for some relative scales. And then a little side thing over here is this, the blue is the habitable zone for people. And if you look carefully, Mount Everest pokes up above that. Not considered habitable on top of Mount Everest, go figure. Why? They are just too thin. There's a density gradient. So all of our activity basically happens in this lowest zone. All of the real fluid action happens in this zone. These zones up above here, up above, well, this came out at the time when Blue Origin and Virgin Space were having this competition about who could send somebody in first. So they both said, well, this guy's neither, well, whether they got to space or not is a different question. But that's how high they get. Okay. So it's a very thin layer. The highest most of us ever get in this thin layer is because we get in an airplane. And that airplane will take you up maybe to this 10-kilometer boundary. 30,000 feet, 35,000 feet. I mean, a lot of commercial flights are at that elevation above the surface because there's no air up there and there's less resistance. So it's a balance between flying the plane and the resistance. So most of us never get much higher than 10 kilometers. I mean, in an aluminum cylinder. Most of us would kind of choke pretty hard to go up 4 or 5 kilometers without this aluminum cylinder. And I've been at 5 kilometers, so I know what I speak of. It's not fun to breathe up there. Okay, now, the world is not a simple place because it spins. So this nice envelope that we created here gets disrupted because it spins and it drags the atmosphere around with it. And that drag then divides, in broad senses, either hemisphere into 3 zones. 3 different convection cells, if you will. Here's the one that we thought of. Up it goes, comes back down. This one doesn't go in the same direction. As this is coming down, this one's got to come down. This one goes along the earth, comes up, comes back down. So it makes the loop. So these 2 complement each other. You can't have one going up and one coming down. You'd have all kinds of nasty thunderstorms. If you go to the higher latitudes, there's a 3rd cell. They're given names. And it likewise is the same sort of rotational sense as the one that's at the equator. Because the Earth is spinning, and because that convection of the cells is going on, we have what's called prevailing winds. Backtracking a little bit, on average we have they're called the Hadley cells. This one's called the Hadley cell. There's the mid-latitude and the polar cell. And really what I want to think about right now, there's an upward and a downward part of them. Here's a zone of ups, there's a zone of downs, zone of up. Theoretically, there's a zone of down right there at the pole. Where is it wet and dry? Cincinnati shirt, and what you read there. What's going to be wet and dry? These things that go, there's circulation going up and down. Where is going to be wet?
Where it's going up,
Why?
because it'll bring the precipitation up with it.
Yeah, the water evaporates from the ocean, gets in the atmosphere gets on a free ride, it goes up. And then it turns out most of it falls back down because when it gets cold enough, the moisture comes back out of the atmosphere. And so your rain belts are right here. What about this area where, so these things start off with some water, but by the time they get up here, do they have much water in them? Gentleman laying back with the, would that cell have a lot of water in it?
If it has a lot of water before.
Yeah, right. It's gonna start off with a lot of water because where it is.
Right,
It's warm here. You're gonna heat up water, you're gonna make steam or whatever, and off it goes, and then.
yeah, so it'll carry water with it, so there would be a lot of moisture in there.
Well, it would if it didn't rain out first. Most of the water turns around because it gets up cold enough that the air can't hold it. So what's left over makes the trip, but not all of
Not
it.
as much.
So this is a wet zone. What's this? A wet zone or a dry zone? Lecture.
For the bottom,
Okay.
like a dry zone.
Yeah. So the areas where this belt used to be carrying a lot of moisture, it gave it up. This one, same thing. So are these zones a lot of precipitation or not? No. Oh, look at that. The Sahara Desert's near one of the downward cells. If we rotated the Earth, we're going to find out Lake Huron's sort of about here. Well, that's going to be another issue. So anyway, these things have these zones. They have pressures with them. These are low pressure, which are typically associated with storms, low pressure storms on top of this general pattern. High pressure is your clear, sunny days. This goes up to sort of 30 degrees latitude north. Cincinnati's about 38, it's about here someplace. So we're in the mid-latitude cell. Individual storms don't pay attention to this traffic system. This is the average. A name that also comes out of this is something called, so we get winds, because the Earth is rotating, the winds don't do this. over Africa, they circle around coming from here to here. In the southern hemisphere, they come from here to here, here to here, here to here. So you get what they call intertropical convergence zone. And the intertropical convergence zone is going to be the theme in the next couple slides. But that's where both of these things converge and where all the rain's taking place. It's slightly off center from the exact equator because of the difference in the amount of land in the northern hemisphere than the southern hemisphere. Here's these wind patterns again in broad senses. Here's our typical winds are the blue, called the westerlies. Here's the easterlies. These zones in between are called the doldrums. They used to have problems getting sailboats across there when they were living on sail powers. Here's the easterlies in the southern hemisphere, and these are the westerlies of the southern hemisphere, which are far stronger than the westerlies of the northern hemisphere. These are going to go through a bunch of land masses. These run around Antarctica uninhibited. So that's the general pattern of the winds. Here's a somewhat same information, but it's in color coded. And so we see some zones here. We see the wind patterns here are phenomenal because there's nothing to break them up. The wind patterns up here are in the same direction, but they're not quite as strong because they don't get wound up as much. You get wind patterns like that over like Russia or North America, but they're fairly calm in many senses. This is how much the wind speed in meters per second at 10 meters above the ground, which is a standard thing. And you see it's not really very windy in most where we are. It's only an average of 4 meters per second or something. Okay, so that's fine. Any questions on that? Gentleman in the black cap, any questions on that? How would you explain this to your friends? Why are the wind patterns where they are? Okay, so do we should we go back to the circulation belts? Do we need to go back that far, or should we want to explain this to our friend? If you can explain it to your friends, you understand it. So do we need to go, does this help? Pattern, why do these circulation belts are doing something funky? They've got this weird angle to them. Why is that? Excuse me? They're pointing towards the equator. They do that, but they also got this curve thing to it. Why are they not just going straight this way or that way? Or more broadly, why do we have 1, 2, 3 cells instead of the conceptual one cell that we drew? Spinning of the Earth, right? The Earth has a tendency to break up this fluid. It breaks it up into 3 different pieces. All right, so when we get wind, these are the average wind patterns, have nothing to do with those on a particular day. And those are the trade winds, and on we go. The intertropic convergence zone, ITCZ, is of special interest. Now I'm going to ask what seems like a stupid question, but I'll ask it anyway. How many of you have ever flown to the southern hemisphere? That's the answer I usually get. I'll tell you one thing. I've spent quite a bit of time here. So every night you leave, well, from one of several airports here, and you leave at 10, 11 o'clock at night or something. About halfway through the flight, you get woken up because the plane starts bouncing like a yo-yo. Why? Because you're in the inner tropical convergence zone, which is where generally the winds want to come up. So right at the equator is all of this activity, and it's shown on here as rainfall. We talked about the rain coming up here because there's a lot of energy. We talked about a lot of it dropping back down, and you can see that right here. Here's all kinds of wetness, But you go up a little bit and it's dry because it's all gone away. It's dry in Africa because there's no water. Here it's wetter than here because some of this can get out of the intertropic convergence zone. Over here, there's nothing to get out of. So this is a bouncy jet ride if you ever have a chance to go to the southern hemisphere. There's thunderstorms all over the place and it's all fun in games. But, and again, it's offset. Now, this also talks about precipitation every year, how many centimeters. So in this zone, we're in the sort of 5 meters, which is taller than this room. That's a lot of water. Cincinnati's in this much precipitation zone. And so we can go through and you can start seeing some of the patterns of wet and dry. And they're not quite simple. Has a lot more to do, the landmass distribution has something to do with it. In other words, this zone isn't dry over here, but this is because Africa's, there's land there. It's fairly complicated in Indonesia because there's also the ocean running around, and in Indonesia you've got 1 billion little islands, and so the patterns get a little more complex. But see, the energy splays off also. So the ITCZ is sort of a fundamental wet spot. That's today's ITCZ. The Earth, on top of this silly spilliness, does something else. It tilts, right? Or the Earth is tilted, or it's not tilted, but it rotates around the sun tilted. The tilt stays the same, but depending on what time of the year you are, the sun being my finger, the rays are different. And so what you see is over several years, this is the actual radiation coming in and going out of the Earth, and you should see a seasonal migration. Now, take a look-see, I'm gonna run it again, but take a look-see at what months the energy's going, and which side, the energy keeps flipping. Whoops, we run out of time, we do it again, yes. No, guess we're gonna do it again now. So we can go back and forth, the hemispheres can go back and forth between adding energy or losing energy just because of this tiltiness and the fact that the heat's being redistributed. So, whoops, that one wasn't there. So you see, even the southern hemisphere, which you think is always cold, at certain months is gaining energy. This is the average. These are in our buddy watts per square meters, which is a number we've seen before. Remember that coming in on the Earth is 340 or something. These are 180-ish on either end of this. So that effect adds into this. The energy changes every season. Well, it's not real surprising then, or maybe it is surprising, but the ITCZ, what we just saw was the yearly average. But the ITCZ migrates every season with that energy balance. And so we talk about the July ITCZ and the January ITCZ. It's by convention because January is the winter in the northern hemisphere. It's obviously the summer in the southern hemisphere. But basically this ITCZ, which we just shown as a straight line across here, has got a bunch of wiggles to it. And they move. And it has a lot to do with the monsoons. This wiggly business in here, when it comes up against the Himalayan mountains, which are about there, it dumps a bunch of rain on India. Okay? Parts of these little blips in here have to do with the configurations of the land masses. So with different land masses, you might get different geometries. If you had a perfect sphere without any land masses, this ITZ would be straight across and it would move back and forth. It wouldn't make any little hiccups here, but it does. But we have land, so we have hiccups. Anybody want to guess where this is going? The ITCC is where it's wet, right? What season of the year might it be the wettest in the Sahara Desert? Or what time of the year? Give you two options.
January?
Okay, this is the belt of precipitation, the intense precipitation. This is the January one. This is the July one. The Sahara's there, which is more likely to provide
July.
the, what we call this, we'll call it July and January to be, because that's unambiguous. But we would think of as the summertime. There's actually the chance to get some precipitation there. Wintertime, not so much. Okay? Now, the ITCZ is built on energy considerations. All right. Gentlemen, way back. What do we have a question about ITCZs? Besides how to spell it, ITCZ, that's it. You don't think you have a question? Can you explain it to your friend? Friends? No, not implying you have a friend. Excuse me?
I think I could.
You think you could? Okay, well, all right. We'll have an audition here sooner or later. All right, so the result of this is that there's a seasonal distribution to the rainfall in Africa. Where are we going with this? We're gonna see it's change in the precipitation patterns. Oh, good, here it comes. What was the month that we wanted?
July.
July. Okay, so here's the rain belt. And this doesn't have all of Africa on it, this is only part of it. And Africa is actually where the ITCE is the most complex because it's a big landmass. It's simple coming across South America, relatively speaking. And here we go. So here's the red is this season, July, and this is the precipitation. Now, it's not exactly over the Sahara, but it's creeping up there. In January, it's down here someplace. So there's no chance in January of getting any precipitation up there. And you see, it's actually not quite so simple. So the ITCZ is one part of it. The precipitation isn't perfectly following the ITCZ, but it does trend with it. It changes with it. We don't need to know why it's not exactly there. I would have to look it up myself to give you that explanation. But what we're trending is that the fact that the rain belt, as they talk about here, and the wind patterns change, and that's fine because it's about monsoons, change. Okay? So now, the wind direction and the rain vary by seasons, not over the land, blah, 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 not line, and it's driven by energy, and the seasonal energy, assuming that the earth is in some sort of balance. Total balance, we're assuming, isn't changing much. We're getting hotter temperatures, that's fine. We're making a big deal out of the energy, out of how many heat records we broke this summer in all kinds of places, but the energy balance isn't changing that much yet. There is a seasonal thing to this. These are the current conditions. What if the energy balance, the larger scale, changed? Do you think these patterns would be exactly the same? Think about it as the ITZs. They're offset because there's a difference in the continents. Continents aren't going to move every season, but if the energy changes, yes, they're going to change themselves. So fundamentally, what I'm arguing to you is that under certain conditions, you can change nuances, not gross scales of where the circulation patterns are. You can't necessarily change, you may not change the season of these, but you could raise this up a little bit so it would go through this area rather than in southern China, or raise this up so it would be maybe impinging on the southern US instead of more in the Central America. And this is a relevation that has not been fully understood, but computer model after computer model these days indicates that as we change the total energy balance of the sun, where these things change matters. And so this is the westerly belt, and you see there's a sort of a limit of it. And this was the question that we were wrestling with right there in South America, is where were the westerlies during sort of the glacial time when the energy balance was cold? Well, it turns out that they had moved towards the pole, and they've moved back. So all of a sudden, these major patterns have a subtle change to them, but can that change the locations of the ITZ, the locations of the wet and the dry? So the seasonal things give us energy changes, give us a clue about larger energy changes that happen over a longer time. That's where I'm going with this. And I think I'm almost gone with this. Conceptually, I've just given you a mechanism to change where the precipitation in dry areas. Subtly, not change it from, not change it halfway across North America or anything. But is it enough to change the balance in Lake Huron and the balance in the Sahara? And I would suggest, for sake of argument, the answer is yes. Okay? Now, let's go to our 8,000 years ago. The world was slightly different at that time, and many people made an allusion to this, and I want to correct a couple of things in that. But as you pointed out, the big energy balance change on this planet is between the ice ages and not. And we know now that the westerly patterns are changing during the ice age. There's always been thought, here's a picture of North America, Cincinnati's right there, of North America with this white umbrella covering called the Laurentide ice sheet. And the real purpose for this is not the details of what the ice cover was, but you got something white there. You got a big white area. So this concept we called albedo, which is the bouncing of the energy straight back, all of a sudden you got a big mirror, huge mirror. There's the mirror today in the northern hemisphere. There's what it used to be. It's a little unclear. It turns out to be a feedback. It got colder for some reasons. This also kicked in. This isn't the main reason it got colder. But because of the albedo effect and the energy coming back up, and the fact that this thing got up to, call it 3,500 meters thick, you have a mountain chain in there that doesn't exist today. The westerlies went from, well, it pushed what in our sense is the wind here from about here down a little bit. So again, it was always thought that it was just the topography of the ice sheet that did this. We now, the physics know that it's the energy. This is 25,000, well this is, we called it 23,000 in here. And this is the time when there's spruce logs up in Sharonville and the ice sheet's right there, and one of those dots is some spruce logs out of Sharonville. All right. And to give you a sense of what this white looks like, that would be what the white looks like. And that's the kind of thing when you walk across it, you get sunburn on your face because even though it's cold, the energy's coming right back at you. So you're getting hit with sun coming in and coming back out. We were going across that one day and we thought we found some bats, which would be the first report of bats in Greenland. Turns out they were lemmings. They crawled up on the ice and they were entombed there for a few hundred years because I don't know why they were on the ice. This is not very close to where lemmings should be, but they were there. All right, so it's white. 8,000 years ago, that big white had started collapsing. And I'm not going to bore you with all the details, but about 8,000 years ago, it was a shadow of its former self and largely centered over Hudson Bay. Okay? So the ice sheet's still in the game, but some of us were wondering if the ice sheet could have changed meltwater into here. And the short answer is no. Even though it was here and it was melting, these waters didn't necessarily come out through here because of the geometry of where the water would drain, and they bypassed the Great Lakes and went out here someplace. I'm not gonna get into the details of that, but. So, the ice is still around, there's still some of albedo, there's still some change in the energy balance. But during the transition, when the world has warmed up to what it's going to be, but it's still adjusting, it took 6,000 years to kill off this ice sheet or something like that. So things are still amok. Now we're at our 8,000 years ago. And what would imply if we have a lower lake level, gentleman sitting next to Liz with the red thing, what,
It would raise,
excuse me?
the lake level would rise, because that's nice.
Well, we started, I mean, it was sometimes when the lake level was higher and then it dropped down, right? It's easy in these conditions to make lake water high because you can put the melted water in and stuff. But getting into closed basins, not so tricky, right? So that tells me that something happened to the, either, back to the question, the delivery of the precipitation or the amount of evaporation. We can still play that chicken and egg question, they're both related, they both probably happen. But now we have a mechanism that would make the Great Lakes dry and would also make the Sahara Desert wetter at the same time, because once you monkey around with one position someplace, it changes someplace else. Anybody not buy that? It's a hypothesis for sale for $1.50 today only. You won't find this in the textbook anymore. Not everybody believes such things. I'm pretty convinced it does work that way. So that's my personal prejudice. Okay. Shall we delve into what we'd like to see for some questions for this to wrap this up and we'll be done with it? Everybody got an answer for that? Jot it down right now, it's fresh in your mind, you won't have to do it later. There's the first question, what does it imply? Or what could it imply? What it has to be about, we talked about the hydrology balance, precipitation, evaporation. Those are tied to the atmospheric circulation patterns. And then the hypothetical, if it was impacted by the atmospheric circulation, is there some way that you could also impact the moving Manford? These are bigger questions. You see how we've built back out, we've zoomed out from Little Lake Huron, which is not little. We're tying it into the global picture, energy balance. And then this is like a give me question, right? Except the succinct part. A succinct sentence, please. And then some sort of bonus question, and I never could decide, I vacillated between which one to make the bonus and which one to make the worth 20 points. But I figured this might be, get more points. I don't know, get more points or not. But anyway, there are two concepts. Must be something else that somebody needs to know about. Okay, let's reconvene on Tuesday. In the meantime, have a good weekend, and we'll see you then.